Hi, and welcome to the 34th day of Just Start Programming, the Rust programming language. Today, we're finally moving on to a new chapter, which is the object-oriented programming features of Rust. So join me once again, live in one take, no shortcuts and no secrets. So let's just start programming. Object-oriented programming features. Object-oriented programming, or OOP, is a way of modeling programs. Objects as a programmatic concept were introduced in the programming language Simula in the 1960s. Oh, that's quite a while. Those objects influence Alan Kay's programming architecture in which objects pass message to each other. To describe this architecture, he coined the term object-oriented programming in 1967. Many competing definitions describe what OOP is, and by some of these definitions, Rust is object-oriented, but by others, it is not. Rust is object-oriented, but by others, it is not. In this chapter, we'll explore certain characteristics that are commonly considered object-oriented and how those characteristics translate to idiomatic Rust. We'll then show you how to implement an object-oriented design pattern in Rust and discuss the trade-offs of doing so versus implementing a solution using some of Rust's strengths instead. Characteristics of object-oriented languages. There is no consensus in the programming community about what feature a language must have to be considered object-oriented. Rust is influenced by many programming paradigms, including OOP. For example, we explore the features that came from functional programming in Chapter 13. In Chapter 13, functional, okay. For example, Chapter 13. Arguably, OOP languages share certain common characteristics, namely objects, encapsulation, and inheritance. Let's look at what each of those characteristics means and whether Rust supports it. Objects contain data and behavior. The book Design Patterns, Elements of Reusable Object-Oriented Software by Eric Gama, Richard Helm, Ralph Johnson, and John Lycides, Addison Wesley, 1994, colloquially referred to as the Gang of Four, is a catalog of object-oriented design patterns. It defines OOP in this way. Object-oriented programs are made up of objects. An object packages both data and procedures that operate on that data. The procedures are typically called methods or operations. Let's try to search this book. Just curious. Design patterns. Published October 21st, 1994. the gang of four. Okay. Using this definition, Rust is object-oriented. Structs and enums have data, and IMPL blocks provide methods on structs and enums. Even though structs and enums with methods aren't called objects, they provide the same functionality according to the gang of four's definition of objects. Okay, so in Rust, you have structs and enums, you have data, and implementation blocks. Encapsulation that hides implementation details. Another aspect commonly associated with OOP is the idea of encapsulation, excuse me, which means that the implementation details of an object aren't accessible to code using that object. Therefore, the only way to interact with an object is through its public API. Code using the object shouldn't be able to reach into the object's internals and change data or behavior directly. This enables the programmer to change and refactor an object's internals without needing to change the code that uses the object. We discussed how to control encapsulation in Chapter 7. Chapter 7, what was there? Growing projects. Chapter 7, we can use the pub keyword to decide which modules, types, functions, and methods in our code should be public. And by default, everything else is private. Yeah, so by default, everything is private, not unless if you specify the pub keyword. For example, we can define a struct average collection that has a field containing a vector of I32 values. The struct can also have a field that contains the average of the values in the vector, meaning the average doesn't have to be computed on demand whenever everyone needs it. In other words, average collection will cache the calculated average for us. Listing 18-1 has the definition of the average collection struct. Okay, so you have average collection, it's a struct, which is public. You have a list which is of type vector containing I32 values. Average is floating point 64. An average collection struct that maintains a list of integers and average of the items in the collection. The struct is marked pub so that other code can use it, but the fields within the struct remain private. This is important in this case because we want to ensure that whenever a value is added or removed from the list, the average is also updated. We do this by implementing add, remove, and average methods on the struct, as shown in listing 18-2. So we have the implementation of average collection. So this is a struct, then you're implementing that one. You have add, remove, and average. Then you have update average. Here, add is a function where it is exposed as pub. So it's also public. This is private. It has a reference to itself, which is mutable, and then you have a value I32 as a parameter. So self list dot push, it will push the value into the vector if you add it, and then calls update average, this one, which is a mutable having a mutable reference to itself, because this one needs to be updated. Let total I32 equals self list iterator, that's sum. So I'm not sure it's an iterator, but perhaps it tries to sum up the values inside the list. And then you have self average total as f64 divided by the length as f64. So that's the average. So average is set. Okay. Then here average will return. So this one looks like a getter. So it will return the f64, which is the value in average. You can also do remove, returns an option. So option will have some or none. How does it return the value? So from list, it will pop the value from the list. And then result is check if you have some value. The value will be here. And then self update average some value. You can update the average. And none. There's nothing left. Okay, so I think the explanation is over here. We leave the list and average. Okay, yeah, so this is the explanation. Because we've encapsulated the implementation details of the struct average collection, we can easily change aspects such as the data structure in the future. For instance, we could use a hash set instead of vect for the list field. Hash set, okay, instead of vect. As long as the signatures of the add, remove, and average public methods stay the same, code using average collection wouldn't need to change. Let's see. Yeah, because add doesn't mention anything about whether list is a vector or a hash set. By having list.push, then it's still applicable for hash set, I believe. If we made the list public instead, this wouldn't necessarily be the case. Hash set and vec have different methods for adding and removing items. So the external code would likely have to change if we were modifying the list directly. Oh, they have different methods for adding and removing items. Oh, so it means push may not be applicable for hash set. If encapsulation is a required aspect for a language to be considered object-oriented, then Rust meets that requirement. The option to use pub or not for different parts of the code enables encapsulation of implementation details. So object-oriented encapsulation, check. Inheritance as a type system and as code sharing. So next one, inheritance. Inheritance is a mechanism whereby an object can inherit elements from another's object definition, thus gaining the parent object's data and behavior without you having to define them again. It's also like reusability. If a language must have inheritance to be object-oriented, then Rust is not such a language. Okay? If a language must have inheritance to be object-oriented, then Rust is not such a language. There is no way to define a struct that inherits the parent struct's field and method implementations without using a macro. Oh, okay. So in Rust, struct you cannot inherit. However, if you're used to having inheritance in your programming toolbox, you can use other solutions in Rust depending on your reason for reaching for inheritance in the first place. You would choose inheritance for two main reasons. One is for reuse of code. You can implement particular behavior for one type, and inheritance enables you to reuse that implementation for a different type. You can do this in a limited way in Rust code using default trait. Yeah, so default trait in traits implementation, which you saw in listing 10-14. So chapter 10, we have traits. When we added a default implementation of the summarize method on the summary trait, any type implementing the summary trait would have the summarize method available on it without any further code. This is similar to a parent class having an implementation of a method and inheriting child class also have the implementation of the method. We can also override the default implementation of the summarize method when we implement the summary trait, which is similar to a child class overriding the implementation of a method inherited from a parent class. The other reason to use inheritance relates to the type system. To enable a child type to be used in the same places as the parent type. This is also called polymorphism, which means that you can substitute multiple objects for each other at runtime if they share certain characteristics. So inheritance, you can see that in traits. Traits in Rust. What about polymorphism? Let's see. Polymorphism. To many people, polymorphism is synonymous with inheritance. Just scroll over here and see. Okay. But it's actually a more general concept that refers to code that can work with data of multiple types. For inheritance, those types are generally subclasses. Rust instead uses generics to abstract over different possible types and trait bounds to impose constraints on what those types must provide. So generics. This is sometimes called bounded parametric polymorphism. Inheritance has recently fallen out of favor as programming design solution in many programming languages because it's often at risk of sharing more code than necessary. Subclasses shouldn't always share all characteristics of their parent class, but will do so with inheritance. This can make a program design less flexible. It also introduces the possibility of calling methods on subclasses that don't make sense or that cause errors because the methods don't apply to those subclasses. In addition, some languages will only allow single inheritance, meaning a subclass can only inherit from one class, further restricting the flexibility of a program's design. For these reasons, Rust takes the different approach of using trait objects instead of inheritance. Let's look at how trait objects enable polymorphism in Rust. Using trait objects that allow for values of different types. In Chapter 8, we mentioned that one limitation of vectors is that they can store elements of only one type. We created a workaround in listing 8-9 where we define spreadsheet cell enum. It's an enum that had variants to hold integers, floats, and text. This meant we could store different types of data in each cell and still have a vector that represented a row of cells. This is perfectly good solution when our interchangeable items are fixed set of types that we know when our code is compiled. However, sometimes we want a library user to be able to extend the set of types that are valid in a particular situation. To show how we might achieve this, we'll create an example graphical user interface or GUI tool that iterates through a list of items calling a draw method on each one to draw it to the screen. A common technique for GUI tools. We'll create a library crate called GUI that contains the structure of a GUI library. This crate might include some types for people to use, such as button or text field. In addition, GUI users will want to create their own types that can be drawn. For instance, one programmer might add an image and another might add a select box. We won't implement a full-fledged GUI library for this example, but we'll show how the pieces would fit together. At the time of writing the library, we can't know and define all the types other programmers might want to create. But we do know that GUI needs to keep track of many values of different types, and it needs to call the draw method on each of these differently typed values. It doesn't need to know exactly what will happen when we call the draw method, just that the value will have that method available for us to call. To do this in a language with inheritance, we might define a class named component that has a method named draw on it. The other classes, such as button, image, and select box, would inherit from component and thus inherit the draw method. They could each override the draw method to define their custom behavior, but the framework could treat all of the types as if they were component instances and call draw on them. But because Rust doesn't have inheritance, we need another way to structure the GUI library to allow users to extend it with new types. So how do we do that? There are no classes in Rust. We have struct. Defining a trait for common behavior. To implement the behavior we want GUI to have, we'll define a trait named draw. Okay, so draw now becomes a trait that will have one method named draw. Then we can define a vector that takes a trait object. A trait object points to both an instance of a type implementing or specified trait. Okay, so instance of a type implementing or specified trait, and a table used to look up trait methods on that type at runtime. We create a trait object by specifying some sort of pointer such as ampersand reference or a box T smart pointer. Then the dynamic keyword and then specifying the relevant trait. We'll talk about the reason trait objects must use a pointer. dynamically sized types and the size trait. Chapter 20. So chapter 20, okay, so it's advanced features. We can use trait objects in place of a generic or concrete type. Wherever we use a trait object, Rust type system will ensure at compile time that any value used in that context will implement the trait object's trait. Consequently, we don't need to know all the possible types at compile time. We mentioned that in Rust, we refrain from calling structs and enums objects to distinguish them from other languages' objects. In a struct or enum, the data in the struct field and the behavior in IMPL blocks are separated, whereas in other languages, the data and behavior combined into one concept is often labeled an object. However, trait objects are more like objects in other languages, in the sense that they combine data and behavior. But trait objects differ from traditional objects in that we can't add data to a trait object. Trait objects aren't as generally useful as objects in other languages. Their specific purpose is to allow abstraction across common behavior. Listing 18-3 shows how to define a trait named draw with one method named draw. Okay, so it's under librs trait draw, and then you have draw function. But if you notice, there's no implementation here. This syntax should look familiar from our discussions on how to define traits in chapter 10. Next comes the new syntax. Listing 18-4 defines a struct named screen. Struct screen that holds a vector named component. This vector is of type box. So I think box is part of smart pointers, yes. So it creates data in heap. But why do we have dynamic draw? What does it mean? This one looks new. Okay. Although we encountered dyn in where was it? I think somewhere in one of these asynchronous implementation. Definition of the screen struct with components field holding a vector of trait objects that implement the draw trait. On the screen struct, we'll define a method named run that will call the draw method on each of its components, as shown in listing 18-5. Okay, so since screen is a struct, we'll implement screen. So implementing screen with a run function, then component in self-components iterator. Once you get component, you call draw. Okay, draw. How does it call draw from here? Vector iterator. What box dynamic draw? This part is not so clear. Okay, this works differently from defining a struct that uses a generic type parameter with trait bounds. A generic type parameter can be submitted with only one concrete type at a time, whereas trait objects allow for multiple concrete types to fill in for the trait object at runtime. Okay, because this is a trait. For example, we could have defined the screen struct using a generic type and a trait bound as in listing 18-6. Okay, so screen using generics. So this is using generics where T is of draw trait. So vector will contain draw trait. And here implementation of screen where T is draw. And then this one is the same as this one. So this one, it was saying that 18-6 is using a generic type and trait bound. Okay, so this restricts us to a screen instance that has a list of components, all of type button or all of type text field. If you'll only ever have homogeneous collections using generics and trait bounds is preferable because the definitions will be monomorphized at compile time to use the concrete types. On the other hand, with the method using trait objects, one screen instance can hold vec_t that contains a box button as well as a box text field. Let's look at how this works and then we'll talk about the runtime performance implications. So box button is referring to, I think it's referring to this approach, while as this part is the explanation for this. Using generics and trait bounds is preferable because definition will be monomorphized at compile time to use a concrete types, which is this. On the other hand, with method using trait objects, one screen instance can hold vec that contains box button as well as box text field. So what are the runtime performance implications? Implementing the trait. Now we'll add some types that implement the draw trait. We'll provide the button type again, actually implementing a GI libraries beyond the scope of this book. So the draw method won't have any useful implementation in its body. Okay, so that's a disclaimer. To imagine what the implementation might look like, a button struct might have fields or width, height, and label as shown in listing 18-7. So you have struct button with height label, implements draw. So draw is the trait for button. So that's why you see draw here. And of course, this is where you implement what will happen to the button if draw is called. The width, height, and label fields on button will differ from fields on other components. For example, a text field might have those same fields plus a placeholder field. Each of the types you want to draw on the screen will implement the draw trait, but will use different code in the draw method, this part, to define how to draw that particular type as a button, as here without the actual GUI code as mentioned. The button type, for instance, might have an additional IMPL block containing methods related to what happens when the user clicks the button. These kind of methods won't apply to types like text field. If someone using our library decides to implement a select box struct that has width, height, and options field, they would implement the draw trait on the select box type as well, shown in listing 18-8. Okay, select box options backstring, so slightly different. Here in button you have label. Implement draw for select box. Our library's user can now write their main function to create a screen instance. To the screen instance, they can add a select box and a button by putting each in box T to become a trait object. They can then call the run method on the screen instance, which will call draw on each of the components. Listing 18-9 shows this implementation. So we're going to define run, screen run. Okay, so we have screen here where you have components of a vector macro. So first one we have box, new select box. So inside box is a select box having width 75. Then you have options. Then here you have button. Okay. Run we cannot see from here, but it's just to represent that run method on the screen instance, which we'll call draw. So assuming that inside you have a screen, where is it? Screen is where? Here. So it will draw. Run draw. So it will call draw on each of the components. When we wrote the library, we didn't know that someone might add the select box type. But our screen implementation was able to operate on the new type and draw it because select box implements the draw trait, which means it implements the draw method. This concept of being concerned only with the messages as value responds to rather than the value's concrete type is similar to concept of duck typing in dynamically typed languages. If it walks like a duck and quacks like a duck, then it must be a duck. Duck typing. That's interesting. Okay. In the implementation of run on screen in listing 18-5, run doesn't need to know what a concrete type of each component is. It doesn't check whether a component is an instance of button or a select box. It just calls the draw method on the component by specifying box dynamic draw as the type of the values in a component's vector. We've defined screen to need values that we can call the draw method on. The advantage of using trait objects and Rust's type system is to write code similar to code using duck typing, is that we never have to check whether a value implements a particular method at runtime or worry about getting errors if a value doesn't implement a method, but we call it anyway. Rust won't compile our code if the values don't implement the traits that the trait objects need. For example, 18-10 shows what happens if we try to create a screen with a string as component. Okay, screen, components, string. Okay, because string doesn't implement run, so it will not compile. We get this error because string doesn't implement the draw trait. Okay, because run is where run draw trait. Draw trait. because run in effect will call draw. String draw is not satisfied, so that's an error. This error lets us know that either we are passing something to screen that we didn't mean to pass and should pass a different type, or we should implement draw on string so that screen is able to call draw on it. Traits objects perform dynamic dispatch. Recall in performance of code using generics. In Chapter 10 are discussions on the monomorphization process performed on generics by the compiler. The compiler generates non-generic implementations of functions and methods for each concrete type that we use in place of a generic type parameter. The code that results from monomorphization is doing static dispatch, which is when the compiler knows what method you're calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can tell at compile time which method you're calling. In dynamic dispatch cases, the compiler emits code that at runtime will figure out which method to call. Okay, so static dispatch versus dynamic dispatch. In dynamic dispatch, the compiler emits code that at runtime will figure out which method to call. When we use trait objects, Rust must use dynamic dispatch. The compiler doesn't know all the types that might be used with the code that's using trait objects, so it doesn't know which method implemented on which type to call. Instead, at runtime, Rust uses the pointers inside the trait object to know which method to call. This lookup incurs runtime cost that doesn't occur with static dispatch. So, moment of truth is here mentioned. By dynamic dispatch, I think that is referring to dyn, if I'm not wrong. Dyn. Yeah, because in this case, draw is the trait object enclosed in box, which is placed inside a vector, wrapped in box. So dyn is the dynamic dispatch. Maybe we look for it later somewhere here also. Dynamic dispatch also prevents the compiler from choosing to inline a method's code, which in turn prevents some optimizations. And Rust has some rules called dyn compatibility about where you can and cannot use dynamic dispatch. Those rules are beyond the scope of this discussion, but you can read more about them in the reference. However, we did get extra flexibility in the code that we wrote in listing 18-5, and we're able to support in listing 18-9. So it's a trade-off to consider. So you get to have the flexibility, but because dynamic dispatch incurs overhead as compared to this approach. Dynamic. Okay. Let's move on. Implementing an object-oriented design pattern. The state pattern is an object-oriented design pattern. State pattern. I think this is the very first design pattern. The crux of the pattern is that we define a set of states a value can have internally. The states are represented by a set of state objects, and the value's behavior changes based on its state. We're going to work through an example of a blog post struct that has a field to hold its state, which will be a state object from the set draft review or published. Okay, so blog post, and then it will have different states: draft, review, or published. Okay. The state objects share functionality. In Rust, of course, we use structs and traits rather than objects and inheritance. Yeah, so structs and traits. Each state object is responsible for its own behavior and for governing when it should change into another state. The value that holds a state object knows nothing about the different behavior of the states or when to transition between states. The advantage of using state pattern is that when the business requirements of the program change, we won't need to change the code of the value. Okay, we won't need to change the code of the value holding the state or the code that uses the value. We'll only need to update the code inside one of the state objects to change its rules or perhaps add more state objects. Okay. First, we're going to implement the state pattern in a more traditional object-oriented way. Then we'll use an approach that's a bit more natural in Rust. Let's dig in to incrementally implement a blog post workflow using the state pattern. The final functionality will look like this. Blog post starts as an empty draft. When the draft is done, a review of the post is requested. When the post is approved, it gets published. Only published blog posts return content to print, so unapproved posts can't accidentally be published. Any other changes attempted on the post should have no effect. For example, if we tried to approve a draft blog post before we requested a review, the post should remain an unpublished draft. Listing 18-11 shows this workflow in code form. This is an example usage of the API we'll implement in a library crate named blog. This won't compile yet because we haven't implemented the blog crate. Okay, so we have main.rs. Okay, it will not compile because we don't have the blog yet. Mutable post new, post add text. Okay, request review, post content, post approve. I ate salad for lunch today. Okay. So this one should be equal to here. It's in here. We want to allow the user to create a new draft blog post with new. We want to allow text to be added into the blog post. If we try to get the post content immediately before approval, we shouldn't get any text because the post is still in a draft. Here. We've added assert equal in the code for demonstration purposes. An excellent unit test for this would be to assert that the draft blog post returns an empty string from the content method. We're not going to write test. Okay, so we're not going to write test for this example. Next, we want to enable a request for a review of the post, and we want content to return an empty string while waiting for the review. When the post receives approval, it should get published, meaning the text of the post will be returned when content is called. Notice that the only type we're interacting with from the crate is the post type. This type will use the state pattern and will hold a value that will be one of three state objects representing the various states a post can be in: draft, review, or publish. Post. Okay. Changing one state to another will be managed internally within the post type. The states change in response to the methods called by our library users on the post instance, but they don't have to manage the state changes directly. Also, users can make a mistake with states such as publishing a post before it's reviewed. Post request review, approve. Okay. Defining post and creating a new instance in the draft state. Let's get started on the implementation of the library. We know we need a public post struct that holds some content, so we'll start with the definition of the struct and an associated public new function to create an instance of post, shown in 18-12. We'll also make a private state trait that will define the behavior that all state objects for a post must have. State trait, okay. Then post will hold a trait object of box dynamic state inside an option T in a private field named state to hold the state object. You'll see why the option T is necessary in a bit. I thought it was going to be easy, but now with all this combination, it sounded complex. But let's see. So you have post, it contains state and content, string, state will return or will hold option, some or none, box, dynamic state. So this part is similar to what's illustrated here. So instead of vec, it was option. So dynamic represents dynamic dispatch. Okay. Option, then you have implementation of the struct post where you have new. So new is for this one, which returns post. So a post having state, some, box, new, draft. Dynamic state. So state should be, oh, okay. So state is not a, no. State is the trait. State is the trait. But here, we have draft. Struct draft. Okay, we have struct draft, which implements state for draft. Okay. Because we have implement state here, so draft is okay. The state trait defines the behavior shared by different post states. Okay, different post states. The state objects are draft, pending review, and publish, and they will all implement the state trait. So aside from draft, we'll have pending review and publish. For now, the trait doesn't have any methods, and we'll start by defining just the draft state because that is the state we want a post to start in. Okay, so maybe let's create a new project. How should we call it? Maybe object oriented. We're done with this, so let me close this. Then terminal. Maybe let's create cargo new object oriented. Then let's do a what's the command again for lib cargo help? Let's see, cargo. Wanted to create a library. Cargo new help. Oops. Let me remove that. We don't need help. Cargo help new. Okay. Here. Create a package with a library target librs. Okay. Cargo object oriented lib already exists. So let me remove object oriented. Then let me do it again. Object oriented. src. Okay. And we also create a main.rs. Okay. And from here we open up Visual Studio Code. No, I don't need Copilot. Make this a little bit smaller. Like that. Size it a little bit. Okay. Then in the lib.rs, let me copy this. Hit here. I don't need that. Oops. Then in main.rs, what's the main.rs? Use blog post. Library create name blog. Okay. Okay. This one is oops. Mod blog. Hmm? Oh, I really forgot. And how do we do that again? cheat sheet. Okay. Source lib. More vegetables. Not from here. Okay, so since in main we have blog, if you wanted to use a create name blog, use cargo add blog and add it to your cargo toml. From source you can create folder blog. Blog we can have mod rs and lib.rs we can copy, put it here. Resolve import blog. Okay. Blog post. Should it be blog? Okay, let me do it again. Let's remove everything under object oriented. Cargo new blog / lib. Okay, let's go to blog. Code dot. Here we have this. So don't be this. Then let's copy. Let's copy this. Okay, and then we need main.rs. We need this. Okay, so we don't have add text content. Okay, so that is fine. Okay, let's continue. So here, okay, new empty string. When we create new post, we set its state to some value that holds a box. Some value that holds a box. This box points to a new instance of the draft struct. Okay, so draft implements the trait. Oops. The draft implements the trait state. Okay, but in our state, we don't have a function yet. Okay. Storing the text of the post content. We saw in listing 18-11 that we want to be able to call a method named addText and pass it a reference to a string slice. That is then added as the text content of the blog post. We implement this as a method rather than exposing the content field as pub, so that later we can implement a method that will control how the content field's data is read. The add text method is pretty straightforward, so let's add the implementation to the IMPL post block. Okay, implement post. Okay, so we can copy this, div.rs, implement post. So I just copy this part, implement post, then here insert this one, add text. So add text, let's check here. So yeah, so now we have add text. So how was it implemented? Mutable reference to self, text as parameter, string slice, content string, push str. So it's one of the functions in string. You have the string slice. Okay. So adding text. Okay, so it can be updated because here there's a mutable reference. Okay, so next, I think that's the description here. We call push str on the string in the content and pass the text argument to add to the saved content. This behavior doesn't depend on the state the post is in, so it's not part of, okay, so it's not yet part of the state pattern. Okay, ensuring the content of a draft post is empty. Even if you've added text, the added some content to our post, we still want the content method to return an empty string slice because the post is still in the draft state, as shown in line 7, listing 18-11. For now, let's implement the content method with the simplest thing that will fulfill this requirement, always returning an empty string slice. We'll change this later once we implement the ability to change a post state so it can be published. So far, post can only be in the draft state, so the post content should always be empty. Okay, so simplest implementation to return an empty string. Okay. Yeah, string slice, content, empty. We calling this somewhere? Yeah, content. So this one is satisfied. Okay, next. Requesting a review changes the post state. Next, we need to add functionality to request a review of a post. We should change its state from draft to pending review. Okay, so request review. So it's still under post. Can add another function here. Request review. Okay, so request review. No method. Struct. Okay. So it means in state we need to have this part. So state, it's inside the trait. The trait is like a contract. If you're using state, then you need to implement this. In this case, it takes in box self and then returns a dynamic state trait. What was the term again for dynamic dispatch? What was that? Let's come back to that. What's it called? Yeah, dynamic dispatch. Okay. Where were we? Okay, so we're here. And then for draft, of course, draft needs to implement it. Yeah, so this one complains because we haven't implemented it yet. Here. Then pending review. So we need another struct for pending review. Pending review. New pending review. What's the trait state is implemented for draft. Box pending review. Okay, we do that. impl state for pending review. Okay, so now it will complain that you need to implement missing members. Okay, but do we have request review for pending review? Do we have that? Let's check here. Okay, struct pending review, state for pending review, request review, also like this, and then okay, so this one is creating a pending review, but this one returns itself. Okay, so let's change to do to self. Okay, so yeah, no need to read this. Okay, at least this part we need to set state to none temporarily rather than setting it directly with a code like self state request review. To get ownership of the state value, this ensures post can't use old state value after we've transformed it into a new state. Okay, where was that? So here it's request review self state equals to sum s. Who is s? Okay, here s is this one, sum s from state take. Then we have take here, this take. State is this state, and then take is from where? Option. Okay, so take is option. If you have sum, so x dot take will be 2. Y would be no. Okay, so it will takes the value out of the option, leaving a none in its place. Okay. So take will takes out the value out of the option. Okay. I think there's some important information here that we need to read. Okay. We give post a public method name request review that will take a mutable reference to self. Then we call an internal request review method on the current state of post. And this second request review method consumes the current state and returns a new state. Request review. Post is post. It's referring to this one. Okay. We add the request review method to the state trait. State trait. Okay, so it's just explaining this part. Okay, here note that rather than having self at self ampersand self or mut self as the first parameter of the method, we have self box self here. This syntax means that method is only valid when called on a box holding type. Box holding type. This syntax takes ownership of box self. Okay, invalidating the old state so the state value of the post can transform into a new state. Okay, so it takes ownership, and having box here, this is a totally new syntax. I'm not sure if it was mentioned in the previous chapter, but it looks new. Only valid when called on a box holding type. Okay, so because box is like a wrapper here, this, and then one important point, it invalidates the old states, so the state value of the post can transform into a new state. To consume the old state, the request review method needs to take ownership of the state value. This is where the option in the state field of post comes in. We call the take method to take the some value out of the state field and leave a none. Okay. So that's the reason why you have take here. Take some and leave a none. Okay. This lets us move the state value out of post rather than borrowing it. Then we'll set the post state value to the result of this operation. Okay, so the state value is changed according to the result of the operation. We need to set state to none temporarily rather than setting it directly with code like substate. Press review to get ownership of the state value. This ensures post can't use the old state value after we have transformed it into a new state. So it's transformed to a new state. The request review method on draft returns a new box instance of pending review. Yeah, it's a new box pending review. Implements the request review method but doesn't do any transformations. Rather, it returns itself. So maybe that's why we have self here. Returns itself itself, because when we request a review on a post already on the pending review state, it should stay in the pending review state. Okay. Now we can start seeing the advantages of the state pattern in request review method on post. It's the same no matter its state value. Each state is responsible for its own rules. We leave the content method on post as is, returning an empty string slice. We can now have a post in the pending review state as well as in the draft state. But we want the same behavior in pending review state. 18-11 now works up to line 10. Adding approve to change the behavior of content. The approve method will be similar to request review method. It will set state to a value that current state says it should have when the state is approved, as shown in 18-16. Okay, so here's the snippet for approve. Let's copy this. Post. Okay, so it's under post request review. We can append it here. Approve. Okay, so approve is missing. So it needs to be here. And we need somebody implementing approve. So here, if you do a quick fix, to insert it. Same for this. And how to implement approve for draft. Approve for draft. Okay, so it will just return itself. Here is draft. Here. Okay, so we can delete this one. It's here. Then my mouse is jumping again. Where was it? Publish, approve is also self. Okay. Similar to the way request review on pending review works, if you call approve method on draft, it will have no effect because approve will return self. When we call approve on pending review, it returns a new box instance. Okay, so I think the pending review. Okay, pending review. Approve will look like this. Pending review, so it's not self, but okay, but now publish is missing, so I'll just copy this part. Okay. But it will not compile, so we need to update the content method on post. We want the value returned from content to depend on the current state of post. We're going to have post delegate to a content method defined on its state. So let's copy this. Let's put here. Okay, so it will not compile yet. So what we need to do to make it compile Because the goal is to keep all of these rules inside the structs that implement state, we call content method on the value in state and pass the post instance that itself as an argument, and we return the value that's returned from using the content method on the state value. What's that? We call asref method on the option because we want a reference to the value inside option rather than the ownership of the value. Because state is an option box, when we call asref an option box, okay, so as reference to the box is returned. If we didn't call asref, we would get an error because you can't move state out of the borrowed itself. Then when we call the unwrap method, which we will never panic because we know the methods on post ensure that state will always contain a sum value when those methods are done. This is one of the cases we talked about in cases in which you have more information than the compiler. Chapter 9. When we know that a non-value is never possible, even though the compiler isn't able to understand that. At this point, we call content on a reference to box as ref. Yeah. Deref coercion will take effect on the ampersand and the box, so the content method will ultimately be called on the type that implements the state trait. So this one. That means we need to add content to the state trait definition, and that is where we'll put the logic for what content to return depending on which state we have, as shown in listing 18-18. Content. So here content is inside the state. Oh, so now we're seeing lifetimes here. Oh, this is getting more complicated. So we put that inside the state. Okay. Trait state content. Well, we still have some issues here. And then here state for published content. Okay, state for published. So by having it here means that draft will use this one. Pending review will also have this as default, while publish will have its own implementation. But we still have some error here. This is all about duplicate definitions with name content. Okay. Is it because of this one? Let's comment this out. Okay, so that fixed it. Okay, so here, let's see, and we're done. Missing 18-11 now works. we've implemented a state pattern with rules of the blog post workflow. The logic related to the rules lives in the state objects rather than being scattered throughout post. So yeah, because originally this is like a placeholder here. It's not supposed to be in post, but rather content should be taken from the state. So if it's still draft, so it will return blank. If it's in pending, it will still return blank. But finally, if it's published, then it will post the content. So we have a lifetime here, post a reference to post.content. So okay, post is here, reference to post is post. Where is post? That was the explanation here. I think it was this one. Reference. So it's extracting the content itself. And then yeah, so content state for published. Okay, so post, once it calls content, it will retrieve the actual content inside post. Yeah, here. Okay. There's some question here. Oh, we are way past the time now, but that's okay. Maybe let's just continue anyway. We're left with some explanation here. Let's just go through, and then after which we can call it a day. All right. So why not an enum? You may have been wondering why we didn't use an enum with different possible post states or variants. That's certainly a possible solution. Try it and compare the end results to see which you prefer. One disadvantage of using an enum is that every place that checks the value of enum will need a match. Yeah, which is yeah, I would say you have to implement each match expression, or similar to handle every possible variant. This could get more repetitive than this straight object solution. Trade-offs of the state pattern. We've shown that Rust is capable of implementing the object-oriented state pattern to encapsulate the different kinds of behavior a post should have in each state. The methods on post know nothing about various behaviors. The way we organize the code, we have to look in only one place to know the different ways a published post can behave. The implementation of the state trait on the publish struct. So that's what we have here. This is where we can get the content. If we were to create an alternative implementation that didn't use the state pattern, we might instead use a match expression on the methods on post, or even in the main code that checks the state of the post and changes behavior in those places. That would mean we would have to look in several places to understand all the implications of a post being in the published state. This would only increase the more states we added. Each of those match expressions would need another another arm. This arm here. Is it referring to the equal greater than sign? With the state pattern, the post methods and the places we use post don't need match expression. And to add a new state, we only need to add a new struct and implement the trait method, and that's that one struct. Okay, so let's go back to the code. It means the pattern here, so draft, pending review, published, and maybe, I don't know, maybe somewhere here you can have it uh, closed, or I don't know, maybe result. So all you need to do is to come up with another struct and implement the state trait. The implementation using the state pattern is easy to extend, add more functionality. To see the simplicity of maintaining code that uses the state pattern, try a few of these suggestions. Add a reject, reject method that changes the post state from pending review back to draft. Require 2 calls to approve before the state can be changed to published. Allow users to add text content only when a post is in draft state. Hint: have the state object responsible for what might change about the content, but not responsible for modifying the post. So these are new requirements. One downside of the state pattern is that because the states implement the transitions between states, some of the states are coupled to each other. If we add another state between pending review and publish, such as schedule, we would have to change the code in pending review to transition to schedule instead. So it's like in pending review, you have a box new to schedule. Box new. Okay, so yeah, just like transitioning to publish, you have a box new. It would be less work if pending review didn't need to change with the addition of a new state. That would mean switching to another design pattern. Another downside is that we have duplicated some logic. To eliminate some of the duplication, we might try to make default implementations for the request review and approve methods on the state trait that returns self. However, this wouldn't work. When using state as a trait object, the trait doesn't know what the concrete self will be exactly. So the return type isn't known at compile time. This is one of the dynamic compatibility rules mentioned earlier. Okay, so request review and approve methods on the state trait that returns self. However, this wouldn't work. Using state as a trait object, the trait doesn't know what the concrete self will be exactly. So the return type isn't known. Okay, so the return type isn't known at compile time. Other duplication includes the similar implementations of the request review and approve methods on post. Both methods use option take. Okay, so the take was to get the sum and replace it with none. The state field of post, and if state is sum, they delegate the wrap values implementation of the same method to set a new value of the state field to the result. If we had a lot of methods on post that follow this pattern, we might consider defining a macro to eliminate repetition. So see macros in chapter 20. By implementing the state pattern exactly as it's defined for object-oriented languages, we're not taking as full advantage of Rust's strength as we could. Let's look at some changes we can make to the blog crate that can make invalid states and transition into compile time errors. Okay, encoding states and behavior as types. We'll show you how to rethink the state pattern to get a different set of trade-offs rather than encapsulating the states and transitions completely, so outside code has no knowledge of them. We encode the states into different types. Consequently, Rust types checking system will prevent attempts to use draft posts where only published posts are allowed by issuing a compiler error. Let mod post new. Post add text. Ate salad for lunch today. Okay. We have it there. We still enable the creation of new posts in the draft state using post new and the ability to add text to the post contents. But instead of having a content method on a draft post that returns an empty string, we'll make it so draft posts don't have a content method at all. That way, if we try to get a draft post content, we'll get a compiler error telling us the method doesn't exist. As a result, it will be impossible for us to accidentally display draft post content in production because that code won't even compile. Listing 18-19 shows the definition of a post struct and draft post struct as well as methods in each. Post, okay, so let's do this. Post struct post content string. Content string. So it means I have to comment this out. Then now draft post. Content string. Then in post, I have this. Post instead of new. Okay, new draft post here. Can comment this part. Replace it with draft post. Okay. Then content. Content will be like this. So what will happen to this one? I can comment this out. Then state. Draft post, implement draft post. I don't like my mouse. Implement draft post. Okay. Both the post and draft. Where is it? Both the post and draft post structs have private content field that stores the blog post text. The structs no longer have the state field because we're moving the encoding of the state to types of the structs. The post struct will represent a publish post and has a content method that returns content. We still have post new function, but instead of returning instance of post, it returns struct post. Because content is private and there aren't any functions that return post, it is not possible to create an instance of post right now. The draft post struct has an add text method, so we can add text to the content as before, but note that draft post does not have a content method defined. So now the program ensures all posts starts as draft post. Draft posts don't have their content available for display. Any attempt around these constraints will result in compiler error. Okay, implementing the transition as transformations into different types. So how do we get a published post? We want to enforce the rule that a draft post has to be reviewed and approved before it can be published. A post in the pending review state should still not display any content. Let's implement these constraints by adding another struct, pending review post. Okay, so another struct, pending review post. Pending review. So let's put it here. Pending review post. Pending review post. Okay. The request review and approve method takes ownership of sub, thus consuming the draft post and pending review post instances and transforming them into pending review post and a published post, respectively. This way we won't have any lingering draft post instances after we call request review on them, and so forth. The pending review post struct doesn't have a content method defined on it, so attempting to read its contents results in a compiler error, as with draft post. Because the only way to get a published post instance that does have a content method defined is to call the approve method on pending review post. Approve method. Okay. And the only way to get a pending review post is to call the request method on a draft post. Sorry, draft post. Draft. Oh, we don't have draft post. Oh, here. Then we call request review. There we have that request review. My mouse is jumping again. Request review in the draft post. Do we have it? Okay. Pending review post. Okay. But we also have to make small changes to main. The request review and approve methods return new instances rather than modifying the struct they're called on. So we need to add more let post. Okay. So to do this, back to main. Salad for lunch. So let's comment this out. Road. insert this part. Okay, the changes you need to make to reassign posts mean that this implementation doesn't quite follow the object-oriented state pattern anymore. Transformation between the states are no longer encapsulated entirely within Rust post-implementation. However, our gain is that invalid states are now impossible because of the type system and the type checking that happens at compile time. Yeah, so it's in compile time. This ensures that certain bugs such as display of the content of an unpublished post will be discovered before they make it into production. Try the task suggested at the start of this section on the blog gray as it is after listing 18-21 to see what you think about the design of this version of the code. Note that some of the tasks might be completed already in this design. We've seen that even though Rust is capable of implementing object-oriented design patterns, other patterns such as encoding state into the type system are also available in Rust. These patterns have different trade-offs. Although you might be familiar with object-oriented patterns, rethinking the problem to take advantage of Rust features can provide benefits, such as preventing some bugs at compile time. Object-oriented patterns won't always be the best solution in Rust due to certain features like ownership that object-oriented languages don't have. Yeah, I think ownership makes it more complex. Summary: regardless of whether you think Rust is an object-oriented language, after reading this chapter, you now know what you can use straight objects to get some object-oriented features in Rust. Dynamic dispatch can give you code some flexibility in exchange for a bit of runtime performance. You can use this flexibility to implement object-oriented patterns that can help your code's maintainability. Rust also has other features like ownership object-oriented languages don't have. An object-oriented pattern won't always be the best way to take advantage of Rust's strengths, but it is an available option. Yeah, so not everything has to be in object-oriented pattern. Next, we'll look at patterns, which are another of Rust features that enable lots of flexibility. We've looked at them briefly throughout the book, but haven't seen their full capability yet. Okay, so let's save that for another day. I think we are way over our allotted time now. So I wanted each day to be an hour and a half at least. But since in this case we can easily cover object-oriented programming if we extend a little bit. We still have some compilation errors here. What is this all about? Request review and approve. I think request review was implemented somewhere. Yeah, so let's save that for another day and see how we can clean this up. And once again, thank you so much for accompanying me in today's topic. I hope you have learned something as well, and hope to see you in the next video. But before that, let me thank my supporters.